Hi, my name is Leonardo Montes Yoca, and I'm going to present the problem. But first, I'm going to show my signature and my name, in which case we have Leonardo Montes de Yoca. Red ID 821664951. There you have it. Okay, so the problem says that the water is pumped from the large tank shown in diagram A below. The entrance of the pipe section is sharp edge and the pipe is cast iron with a total length of 2 meters. The flow within the pipe is also to observe to be fully turbulent. We know that when we have fully turbulent flow, we're looking in the book and in the spectrum, it tells you where you are on the laminar and turbulent. And we know that if we're fully turbulent, we can go back to our diagram. What I mean by diagram is the Moody diagram, and look for the fully turbulent region. And from there, just straight up get the friction factor. But in this case, I will be solving for it to show a different way. The next portion says the relationship between the volumetric flow rate and actual head rise is provided in the pump specifications as shown in diagram B. So here we have diagram B, in which in turn, it shows that the relationship between the volumetric flow rate in meters cubed per second, as well as the head rise of the pump in meters. And this specific equation relates to two. This specific is, and it's the graph, represents the graph, which in turn reads 20 minus 2,000 Q squared. Another important detail to notice is that at this dot here, we have a higher flow rate than at this dot. And that when we have a higher flow rate, that our water is almost moving as fast as our pump blade, so the pump doesn't really require as much work to get going. However, if you have a flow that is slow, the pump blades are going to be able to absorb more of that force, and so we are going to see more of a head rise when observing the slower flow rates. So I like to kind of think of it as a car. When you're trying to get a car to accelerate, it's going to be harder to make that happen when it's stationary versus when it's moving at a really high speed. So it's the same thing with these blades when the fluid going into contact with them. Anyways, I'm going to read portion A, which says, determine the volumetric flow rate for the system. Okay, so I'm just going to write it all out here. So Z1 minus Z2 would be 6 meters. Okay, and our one subscript and our two subscript are denoted by this portion at the top and portion at the bottom with this length. Okay, so the next portion, I kind of like to write things out. So we know that the diameter of the pipe is equal to 0.07 meters and that the length of the pipe is equal to 2 meters. We also know that they tell us that it's cast iron. So it's going to have a factor of 0.26, which in turn would be 0.26 by 10 to the third meters. Looking also in the book looking also for our KL would be 0.5. So all these are important details to help us solve the problem. The next portion I'd like to explain is that we are going to put the energy equation between point 1 and point 2. With so that being, it'd be P1 over that symbol over V1 plus. Okay, I'm just going to write it out and explain, then I will explain how I got to those points. So this is plus Z2 plus HL. Kind of ran out of room there. Anyways, we know that our tank, since like in the picture it showed it open to the atmosphere, so it's gonna be, we're gonna have our P1 equal to P2, which is equal to our pressure of atmosphere. It's our first detail. And so that case we can cancel these out, make them 0. So it's 0 because open to the atmosphere. Next portion, for the next part, we can cancel this art here because of the tank sizing specifically, we can make this negligible. So V1 over 2G squared, tank sizing. That's why it became 0. So these are why it became 0. The next portion is I would like to take into account this plus sign. This plus sign here is because we're not extracting anything. We're not really taking energy from what's happening in this case. We're where in another example, we had a turbine extract energy from the fluid. But since we have a pump, we're gonna add. Then we have everything we need to do. We have everything, every one of these variables is what we are gonna be needing. So then we can simplify that to get Z1 plus head of the pump V2 squared over 2G plus Z2 plus HL. Simplify it even further to get H of the pump equals V2 squared over 2G plus Z2 minus Z1 plus HL. So throughout the whole thing, the average velocity of the pipe would be V, so we can just replace our V squared with V minus, and we're just gonna plug in the values. Okay, so we have this equation. We have this HL here on the outside. In which case we need to notice that we have our HL of our major plus our HL of our minor, because it's the full piping system, or the full system. You know, changes in the full system is major and minor. Okay, so then but then that isn't and that's where I'm going with the friction factor solving for it, because both of these contain the friction factor. I'm sorry, one of them does. The other one has our K value that we figured out earlier. So yeah, I'm going over to this. I'm just gonna write out what our plug in our values for our HL major, which would be F 2.0, which is what they gave us, 0.07. Also given, changing point because that's what they gave us at the beginning, right? So it'd be 0.07. And our 2 meters with the length. Just plugging in here. So we have V squared over 2G. HL minor would be 0.5 V squared over 2G. And that's what we found earlier from the K value that we found earlier. Therefore, I'm going to simplify this. We get HL. After simplifying that, we get HL is equal to frictional factor 285.714 plus 0.5 V squared over 2G. So I'm just plugging in and simplifying to what I wrote about HL minor plus HL major. Okay, so then so for the pump, so the so H of the pump is equal to V squared over 2G. We do this relatively quickly because I want to run out of time. 285.714 plus 0.5 V squared over 2G. Okay, so simplify that even further. 285.714 Okay, that's the simplification for that. And I just want to plug in what I mentioned earlier about relating the equations on the graph, which I said that Q would be 20 minus 2,000 Q squared as the reading that's shown on the graph. So we just plug that into this equation here, okay, which H of pump. We just plug that in here, in which we could do 20 minus 2,000 Q squared V squared over 2G 1.5 plus 285.714F. Okay, so now I'm just going to simplify this even further. V squared. I'm sorry, if it didn't read, that's what it is. I just plugged that into here. Okay, there we go. 285.714. It's harder. It's really harder to write when I get lower down on the paper. But yeah, that 20 goes to 40 because we subtracted it, from the 20 from the other side. I guess, so yeah. So then after that we have this equation, we do Q. We recognize Q is equal to area times velocity. So area, velocity. So our area would be pi over 4 by 0.7, the diameter, times our V, velocity. which we would end up getting 0.00385 V. This is a very important detail at the end to solve. Okay, so then now I'm going to move on to the next step, okay, because we got to figure out a set of equations to solve for this thing using our Reynolds number. So I'm going to do that portion now really quickly. So do negative 2,000, plugging in what we just, by plugging, and all that by plugging in what I just solved for. 1.5 plus 285.714F minus 40. So then we get negative 0.029645 V squared equals V squared over 2G. What's in the brackets for F minus 40. Okay, so then now we're going to rearrange it to get 0 on the one side. Okay, so then 14,5,624 VFV squared minus 40. Okay, and we get 40 is going to be equal to 0.106095 V squared plus 5,624 FV squared. Okay, so then we get V squared 0.10695 plus 14.5624 F. And that's what we have. I'm sorry, this would be 40. So then now we simplify it even further to get V squared equals to 40, 0.10695 plus 14.5624 F. This would be E1, equation 1. That's why that means. Then we solve for Reynolds number, which we have the equation for that to be RE equals rho VD over mu. So then we plug in 998 by V 0.07, 1.002 by times 10 to the 3, as we can solve for from as we previously explained. So it'll be 6972056 V for equation 2. So we have this equation and this equation. Okay, so now with those two equations, so the flow, so we know the flow is turbulent, so that we can use a Colebrook equation to find the friction factor is what I'm getting at here. And I'll just write it here like so. Okay, so then so what I did is I just plugged in, I did E1, equation 1 over equation 2. I mean, not E1, I'm writing it like this, E1 and E2, and plugged it into this equation to solve for RE. So this is 697205640 over, I'm running out of room, but this is going to be 0.10695 plus 14.5624 F. That's just, so that's the equation here. I just put that under there because I ran out of room. But anyways, so yeah, just using the values to plug it into one another and to get that equation that I will to solve for. Okay, so now we have 44951.54 all over. Just gonna write it out cleaner. That kind of stressed me out a bit, and I kind of lost my point. 14.5624 F. So that's just clean up the equation. Therefore, we can do 1 over F, plug it back into our other equation that we started with, the Colebrook one that we started with. 0.26 by 10 to the negative third. 0.7. Okay, plus, I'm just going to continue on this next line. 2.51 over 44095.54 all over, this mess goes here, by F. Yeah, this is a lot of simplification, but when I went and simplified it even further, found the friction factor to be 0.028. And that's necessary because we needed to plug it in back into V squared equals 40, our earlier equation, which contained these values. Okay, so then we have this equation, which is what we solved for literally here. So then we can plug in what we found for F, because we plug that into our Colebrook, and we can then solve for that value to get our V. So after solving for V, we plug in this F here, and solve for V to get 77845. So then we simplify that V squared to get our final velocity of 8.823 meters per second. So our volumetric flow rate would be Q, as we solved for earlier, 0.0385 V. That's why I said that was a very important step, because now we can plug in our V into this equation here. To get our value of 0.034 meters cubed per second. And boom, boom, boom. That's good. So then now, that's all the work we had to do for part A. So now I'm going to solve for portion B, which says, to show that the observation is fully turbulent, flow was correct. So in order to do this, we really have to set up what we call, we have to work with Reynolds number. So then so we solve for Reynolds number to be equal to 6972.56 V earlier when the equation, we solved for it to be that value earlier using the Reynolds equation. So then after that, so that's our Reynolds value. So then what we did after that, we can just plug in our V from our last example, which literally from a couple of seconds ago, to be 8.823. So it'd be 61544.5 would be greater than our RE at 4,000. So in fact, we just use an arbitrary 4,000, and since this value is higher than that one, we know we have the turbulent flow. I'm doing it fast because I'm running out of time, but anyways, for the next portion, for portion C, they say if the pump is 70% efficient, determine how much power must be supplied to the pump. So the power, we can just, from this point, I'm not going to go back, but because we know we have these values solved from earlier. All these values I'm going to plug into this equation is from what we solved for throughout this whole problem earlier, using this equation, rho G HQ over L. So then we can solve, we have our H. For our H, we can do 220 minus 2,000 times 0.034 squared equals 17.688 meters to solve for our height. Okay, we use what we found in what was in the graph, as well as what we saw, this value that we used earlier to solve for our height. So then now we can do W, plug in all these values to get 998 by 9.81 by 17.688 by 0.034 all over 0.7 to get 8411.223 watts, which in turn gives us 8.411 kilowatts. And that's our answer for portion C. Thank you.